I will then present my entire screen. All right. Okay. Before I get going, I just have a question to ask those individuals at home. Do you see just the presentation right now? If you could respond, please.
Yes.
Yes. Excellent. I am so smart. Okay, that's all I needed to know. So what section 5 is dealing with is called calorimetry. All right. So far, in the last couple of sections, we've talked about internal energy and how we can look at the change of internal energy of a system. We just most recently talked about change in enthalpy, to where we can actually measure the change in really energy as a process proceeds by measuring the change in temperature. So that gives us a really good insight into how energy is flowing in certain scenarios. And so since we cannot know the exact enthalpy of reactants and products individually, what we can do is measure the change in enthalpy through this calorimetry. And this is what we're going to be doing for our lab, is calorimetry. We're going to be measuring how much energy is there in various types of food. And we do that by measuring the change in enthalpy, or change in heat. Okay, is the temperature of the surroundings going to be changing from higher temperatures or lower temperatures? So we're measuring heat flow. And it's important to remember when we are measuring calorimetry that we keep in mind that we are measuring the temperature of the surroundings. Okay? So what we need to do, we always have to keep in mind what's happening in the system. Okay, early in this chapter, we talked about system and surroundings. The system is our focal point where reactions are taking place. The surroundings are everything else, okay? So a lot of our stuff is going to be taking place in aqueous solutions, okay? It's going to have a reaction inside water, or we can just use water itself in order to measure heat flow. So this is where a new concept comes into play called heat capacity or specific heat, okay? By definition, specific heat or heat capacity, they're really one and the same, is the amount of energy required to raise the temperature of a substance by 1 Kelvin. Again, Kelvin is really the scientific measurement of temperature, or 1 degree Celsius. What do you notice about those two numbers right there? Okay, right here. 1 and 1. What are they? Okay, we're gonna get woken up here. They're the same number. Okay, so really these numbers are interchangeable, or these letters are interchangeable. Okay, it's a 1 to 1. Sometimes in some problems you're going to be given temperatures in Kelvin. Sometimes you're going to be given temperatures in Celsius. It doesn't matter. There's no big conversion needed. All you got to do is change the letter. Okay. Now, the higher or the greater the heat capacity of a substance, if you notice here, like N2 in the table below is 1.04, and it has units of joules per gram Kelvin. Okay. So the unit of specific heat gives us some insight also as to what units we're going to have to use, let's say if we ever have to calculate it, like we might hear in just a few moments. So nitrogen gas has a specific heat of 1.04. Aluminum, it's a metal, 0.90. So the greater or the larger the specific heat value, the more heat energy is going to be required to increase it by 1 Kelvin or 1 degree Celsius. Okay. H2O is a liquid. That's a very popular one. That's one we're going to use a whole bunch. 4.18. In fact, it's a little more specific than that, and you're going to see here in just a moment. Okay. So it takes 4.18 joules of energy to raise 1 gram of water 1 degree Celsius. And I actually like this definition better than I do the previous slides. Okay? So if you ever have to know a definition for specific heat or heat capacity, again, one and the same, it's this slide right here. Because it goes a step further. It says the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius. So for instance, if we look at this image on the right-hand side, if we have 1 gram of liquid water, its current temperature is 14.5 degrees Celsius. It's going to require 4.184 joules, which is also equal to 1 calorie that we've seen before, of heat in order for that 1 gram of water to increase to 15.5 degrees Celsius. So that's why I like this slide better. It kind of gives a better viewpoint of what specific heat is. Now, there is a really simple and basic formula that we can use to help us in calculating specific heat. Okay? And another good thing about it is it's going to look very similar, in fact, to the calculation formula that we're going to use for calorimetry, which we're going to dive further into calorimetry tomorrow. It's going to be a real quick discussion tomorrow. You'll have time in class to work on your problem set. But there's one small difference between the two, and it's because of the vantage point, okay? How you are looking at the scenarios, all right? So in order to calculate specific heat, I want you to highlight, star, arrow, whatever you have to do to this slide. I want it to be able to call out to you. In order to calculate specific heat of a substance, you simply take the heat transferred divided by the product of the mass of substance that you have multiplied by the change in temperature. Or to put it in more of a formula viewpoint, S for specific heat is equal to Q, which again is heat transferred in joules, times, or divided by M times delta T. If you think about it, look at these units, joules per gram Kelvin. Joules per gram Kelvin, or this could also be degrees Celsius, okay? So the formula for specific heat sets up the units in the appropriate form. Now, with this being a formula, what does that mean? Well, that means we can also rearrange this formula to solve for any of these variables listed in here. Again, it's just referring back to algebra. So what we're going to do, we're going to take this formula for specific heat, we're going to do some practice with it. Tomorrow, when we get into calorimetry, we're going to have this basically the same thing, except it's going to be rearranged to solve for Q. There's also going to be another element in there, because when we talk about calorimetry, we have to think of sign conventions. Is it positive or negative? And the fact of what we're measuring, okay? We're not measuring the system, we're measuring the surroundings when we get into calorimetry. That's all I'm going to talk about calorimetry right now. I want to look at some examples here. Now, I will say that in this two-part question, part B, I don't necessarily ask you questions, say on a quiz or a test about. You might see it on a question in the problem set. So I'm not going to spend a whole lot of time in it. I'll just show you how to go about it. It's very simple, very quick. But let's look at part A at least first. Part A says how much heat is needed to warm 250 grams of water, which is about 1 cup, from 22 degrees Celsius to 98 degrees Celsius, which is near its boiling point. So we need to figure out the heat capacity, how much heat is needed. So that means that we need to solve for Q. Again, heat, okay? It doesn't say solve for specific heat. It says solve the heat needed. So we're solving for Q. So just a few things here. First, we need to determine what was the overall change in temperature. And so when you calculate your change in temperature, you take your final temperature minus your initial temperature. So your final temperature is 98 degrees Celsius. Your initial was 22 degrees Celsius. So subtract 22 from 98, you get a temperature change of 76 degrees Celsius or 76 Kelvin. Okay? So as you rearrange this equation to solve for Q, you're going to have the setup where we're going to have specific heat times mass times temperature change. Now, I don't know why your book did this, but as you notice here, you've got this CS right here. Okay, right where my little arrow pointer thingy is. In fact, I'm going to get this guy right here. Don't let that throw you off. That's just another way to indicate specific heat. Okay? If you ever see that, that just means specific heat. C sub S, okay? So, formula to solve for the heat required is Q equal to specific heat times mass times change in temperature, like I mentioned. And since we are talking about water, and water's specific heat is right here. So we use that value, multiply it by our mass of our substance. And notice something here. You got to make sure that your mass is in grams. That way the appropriate units cancel out. All right? And then we multiply it by our change in temperature of 76 Kelvin. And we find that it requires 7.9 times 10 to the fourth joules of heat to increase that amount of water by 76 Kelvin. Okay? That's how much heat has to be put into it. And don't forget your labels. Heat is energy. Energy is in joules. Okay? So that would be your answer for part A. Part B says, what is the molar heat capacity of water? Again, I don't necessarily ask you this, but you might come across it in your problem set. All you simply have to do is this. First of all, by this point, you should know how much, the molar mass of water is. Okay, 18 grams per mole. So you take your molar mass of water and you multiply it by the specific heat of water, 4.18 joules per gram Kelvin. Cross out the grams unit. It gets replaced with the mole unit. And your molar heat capacity is 75.2 joules per moles Kelvin. So again, take the molar mass of a substance, multiply by its specific heat, you have your molar heat capacity. That's that. Okay? Let's look at a couple other examples now. Yes, two-part question. And I'll be doing this on the little whiteboard. So large beds of rocks are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram Kelvin. Calculate the quantity of heat absorbed by 50.0 kilograms of rocks in their temperature, if their temperature increases by 12 degrees Celsius. Okay. So I'm going to utilize my little whiteboard. Okay. Let's look at a few things here. Okay, all right. So first of all, it's asking us to figure out how much heat is going to be required. Okay. So we're going to be rearranging our equation to solve for Q. So Q is equal to S times M times delta T. So a lot of times when I have formulas, I like to, identify what values go with each variable. So just off to the side, I'm just going to rewrite all of my units. Okay. So again, right now we are talking about large beds of rocks, okay? And they give us the specific heat of the rocks, okay? They give us at 0.82 joules per gram Kelvin. So for our specific heat, our S is 0.82 joules per gram Kelvin. Our mass, we are told, was 50 kilograms. What should it be? What unit should it be in? Grams, okay? Very good. Because our specific heat has grams in it, we got to have grams as well. So in order to go from kilograms to grams, we're simply going to convert 1,000 grams divided by 1 kilogram, and we're going to get 50,000 grams. In our last bit of information, our change in temperature, we are told that it was 12.0 degrees Celsius, but we could also put 12.0 Kelvin. Again, it's just as easy as swapping out the units. So now I've got everything that I need to solve for this problem. Okay? So now I'm going to simply go ahead and solve for Q. And so my specific heat, again, was 0.82 joules per gram Kelvin. My mass was 50,000 grams, which grams can cancel now. And lastly, our change in temperature of 12.0 Kelvin, which Kelvin is going to cancel out now. It's going to leave us in joules, which is the appropriate unit for Q. So I want you to check my work. Okay, go ahead and multiply all these through. But when it's all said and done, you should have a total heat quantity of 4.9 times 10 to the 5th joules. Double check my work before we proceed. Is it looking okay? Is it looking good? Excellent. So that's what your answer would be. Circle it, move on. Okay? Now, this, like I said, this is a two-part question. So I'm going to go ahead and erase this now. Okay? I'm going to keep my little variables on the side here because I have a feeling we're going to be dealing with very similar stuff. Oh, before I get into that, though, I have a story I figured you'd all appreciate. So yesterday, towards the end of the day, I'm cleaning my boards, and I haven't been cleaned in a while. In fact, I hadn't changed the backboard since November, so I had to use that whiteboard cleaner spray, and it's got some chemicals in there, right? So I come up here, and I'm talking to my wife as she's taking one of my daughters to her eye appointment, and I'm sitting there spraying off here, and I'm not paying attention. I go to put the bottle up there and spray my whiteboard up front. Apparently, my finger had turned the nozzle, and I got just a face full of cleaner spray to end my day yesterday and to get me prepared for everyone to come back. So, you know, we can't all start off on a really fantastic foot, but we can make up for it. And it only burned for a few minutes, so no biggie. Anyway, all right, part B. What is the temperature change? Oh, sorry. What temperature change would these rocks undergo if they emitted 450 kilojoules of heat? Okay, so going to be solving for something different now. We're going to be solving for the change in temperature that would be needed what would happen to the change in temperature if we release 450 kilojoules of heat. So back at this again. So this time we're solving for delta T, okay? The mass is going to stay the same, and we're just going to go ahead and write down 50,000 grams, okay? The specific heat, again, is 0.82 joules per gram Kelvin. Now, the heat this time is 450 kilojoules. But kilojoules is not the appropriate unit since we're dealing with specific heat that is in joules. So we need to take that 450 kilojoules and again convert it by taking 1,000 joules divided by 1 kilojoule, and you're going to get 450,000 joules. Okay, so we've got everything here. So really what we're going to need now, again, if we have this equation, the general equation, I need to solve for delta T. So in order to do that, I'm going to rearrange it by multiplying both sides by delta T to get it out of the denominator. So I'm going to get S times delta T is equal to Q divided by M. And then my last step, divide both sides by the specific heat to where I get delta T is equal to Q over M times S. So just a little bit of algebra rearranging, and now I can go ahead and plug in my values. So again, my Q was 450,000 joules. My, excuse me, mass, again, was 50,000 grams. And my specific heat was 0.82. Okay. So, again, check my work. And what's odd about this particular question is the answer has changed from year to year. I've had some disagreements, and I don't know why. But the last question that we did was we got 11 Kelvin. Double check my work. Is that what you got? You're not done yet? What'd you get? Try it again. So what I would do is take the 50,000 and multiply by 0.82. Okay? And then hit equal. And then do 450,000 divided by then second answer. $11. Yay! Did you get that time? Excellent. Perfect. So you're going to have a temperature change of about 11 degrees. So that's how you calculate specific heat, okay? Now, just to give you a taste of what we're going to be looking at tomorrow, and then I'm going to call it quits, is, again, tomorrow we're going to be specifically talking about calorimetry, where, okay, if we were to look at calorimetry, let's say the system, which is like the chemical reaction is taking place is right here, inside water. We are going to be measuring the temperature change of water. So when we are trying to determine what's happening in the system, we have to just simply add a minus sign, because that's going to keep the convention of what's happening in the system. Because if the water, which is the surroundings, increases in temperature, what did the system have to do? Did the system release or absorb energy if the water got hotter? Imagine if there was an explosion in water and that water got warmer. What happened to that energy? It was released. Okay? And when you have the system releasing energy, the overall heat transfer is going to be negative because it's releasing it. And it makes it exothermic. And the vice versa is going to work as well. But that's why when we are talking about calorimetry, we take that same formula, but simply add a minus sign in there. Okay? But we'll talk more about that tomorrow. And we are going to stop presenting, and we are going to stop